Thank you for being here today. In this presentation, we'll be exploring two important concepts in machine learning: how to measure success effectively and how to avoid overfitting in your models. In the world of machine learning, just like in policymaking, it's not enough to gather data, we need to measure whether our models or strategies are delivering meaningful results. We'll begin by discussing the process of measuring success across different types of machine learning: supervised, unsupervised, and reinforcement learning. I'll show you how focusing on the right data is essential to making accurate predictions or identifying useful patterns. Afterward, we'll move on to the concept of overfitting, a common challenge where a model becomes too specialized to the training data and fails to generalize well to new situations. I'll walk you through how overfitting affects supervised, unsupervised, and reinforcement learning, as well as the strategies we can use to prevent it. Ultimately, these two concepts are foundational in ensuring that our machine learning models are both accurate and adaptable, leading to better decisions in complex environments like public policy. So, let's dive in and explore how to achieve meaningful outcomes while avoiding common pitfalls in machine learning. Measure success. Once you've identified the most important data to focus on, the next step is to determine how to measure success effectively. Just like in policymaking, it's not enough to gather information, you need to measure whether your strategy or model is actually working and delivering results. In supervised learning, success is about making accurate predictions. But accuracy depends on how well you focused on the right data. For example, if you're using historical tax data to predict the impact of a new tax law, your model's success will be measured by how accurately it predicts changes in revenue. However, the accuracy of that prediction hinges on whether you focused on key factors like income brackets and business revenues rather than irrelevant data like the number of parks in a city. In unsupervised learning, success is measured by how well the algorithm finds patterns or groups, but again, it depends on what data you used. If you're analyzing traffic data to find patterns in congestion, the algorithm's success depends on whether you focused on traffic volume, road capacity, and time of day, key factors that meaningfully contribute to the problem. If you used irrelevant factors, the groups or patterns the algorithm identifies won't be useful, so success can only come from focusing on the most relevant data. In reinforcement learning, success is about continuous improvement over time. For example, if a system of smart traffic lights is adjusting itself based on real-time traffic data, its success will be measured by how much it improves traffic flow over time. But again, this success depends on focusing on the right factors, like traffic density, vehicle speed, and road conditions. If the system instead focused on less relevant data, like pedestrian clothing styles or vehicle colors, it wouldn't learn effectively, and traffic flow wouldn't improve. Ultimately, measuring success in machine learning, just like in public policy, requires not only setting clear goals but also ensuring that you've focused on the right data from the start. By concentrating on what truly matters, you increase the likelihood of achieving meaningful, accurate, and useful outcomes. Avoid overfitting, don't overfocus on the past. Today, I want to talk about a critical concept in machine learning called overfitting. Overfitting happens when a model learns not just the useful patterns in the training data but also the noise and irrelevant details. Imagine trying to memorize every single word of a speech instead of understanding the main ideas. When a model overfits, it performs well on the training data but poorly on new, unseen data because it becomes too specialized and rigid. Supervised learning. Let's start with supervised learning. This is where we train models using labeled data. Overfitting occurs when the model learns too much from this training set. For example, consider a model designed to predict the impact of a new education policy on student performance. If the model is trained on specific test scores and demographic details but overemphasizes minor variations, like an unusually high score from a single school, it may fail when applied to a broader population with different characteristics. To avoid overfitting in supervised learning, we can use several strategies. Cross-validation. This involves testing the model on different parts of the data to ensure it works well across various scenarios. Regularization. By introducing penalties for overly complex models, we encourage simpler ones that focus on key patterns. Pruning. In decision trees, we can trim unnecessary branches that don't contribute to better decisions. Choosing simpler models when we have limited data. Opting for simpler models can help reduce the risk of overfitting. Early stopping. We can monitor performance during training and stop when it starts to decline. Unsupervised learning. Next, let's discuss unsupervised learning, where we identify patterns in data without labeled outcomes. Here, overfitting can happen when the model identifies patterns that aren't actually there. For example, think about using clustering techniques to group citizens based on survey responses regarding public health initiatives. If the algorithm focuses too much on irrelevant details, like the specific wording of survey questions, it may create groups that don't accurately reflect meaningful differences in health needs. To prevent overfitting in unsupervised learning, we can reduce dimensions, focus on the most important features to simplify the data, and reduce noise. Choose the right algorithms. Use algorithms that are less prone to overfitting, like k-means clustering. Set clear evaluation goals. Use our understanding of the data to define what makes a good pattern. Regularization. Keep the model simple and focused. Reinforcement learning. Finally, let's look at reinforcement learning. Here, we train systems to make decisions based on feedback from their actions. Overfitting occurs when a system only learns to react to specific situations. For example, consider a traffic management system that optimizes traffic flow at intersections. If it learns to respond only to specific traffic patterns during peak hours, it might struggle during unusual situations, like a parade or an accident, leading to inefficiencies in managing traffic. To combat overfitting in reinforcement learning, we can balance exploration and exploitation. We need to encourage the system to try new actions while still optimizing known successful ones. Use experience replay. Storing past experiences can help the system learn from a variety of situations. Regularization. This limits how complex the system can become. Curriculum learning. Start with simpler tasks and gradually introduce more complex challenges. Transfer learning. Applying knowledge from similar traffic patterns in different cities can improve adaptability. In conclusion, overfitting is a common issue across all types of machine learning, including applications in public policy. By using these strategies, we can ensure that our models are more robust and effective, leading to better decision-making based on data. The key is to strike a balance between being complex enough to learn important patterns and simple enough to generalize well to new situations. Thank you.